Cool. So yeah, sorry. Working. So yeah, experiment number 2 in working outside because of construction. But yeah, let me screen share, and then it's the link is just like it is all the other weeks, but I will post it in the chat, which is github.com/jpowerj/DSUA111-sections. Pasting it now. Cool. So it's in the chat, and but just like last week, I finally figured out how to like publish the actual screen, the actual slideshow. So if you go to that link, you'll see like down week 4, like I just did, you can click a link to find these slides, right, and follow along with them live. Or if that doesn't work for you, or if you just want to download it like for offline use, you'll see the link to PDF slides and just the link to the like source notebook, right? Both the PDF slides and the slideshow come from this Jupyter notebook. Wait, can people say in the chat if they can hear me, maybe? I'm very scared. Okay. Thanks. Yeah, amazing. Thank you. Okay, cool. So let's start because, yeah, it's a packed day. Amazing. Thank you, Evie and Lila. Cool. So great, and you'll see both of these links down here, right, to this specific slideshow, like for following along, but then also just all the materials. Cool. So let me just go right into it. That homework 1, there have been some ridiculous changes made to the course administration by some of the Center for Data Science authority figures, let's say. And now, instead of getting your homework back to like 24 hours after you submit it, now it's going to be a week. So you will get your homework 1 scores back by end of day on Monday, like beginning of next week. Yeah, the class, it's pretty weird. It just went from like a class where like all the TAs and the professors would like meet and stuff and talk about things to like a fully top-down thing this semester. Yeah, I ranted a lot about it in my last section, and I don't know, to minimize chance of getting fired, I guess that's all I'll say. But yeah, it's not good. I don't think it's very good for you or learning because everything's all like misaligned. Like I got a lot of questions last section on like, wait, how do we do like homework 2? It says it's due October 12th, but we're not even going to be done with all the like part 2 topics by then. I hear you, is my response to that. Like, we're trying, but it's just a very weird like structure this semester. Yeah, I guess it's okay if I get fired, but I'm gonna go ahead and just, you can ask me about it later. But I'm happy to complain about it, is what I'm saying. Cool, but just going into it, like, yeah, you'll get your, yeah, that's another thing, sorry. You won't get like a feedback document. Like that's what we've been doing the last 5 semesters, but for some reason, it's not good this semester. So instead, you're just gonna get a numeric grade on NYU classes with like feedback. Like I'll type feedback. I actually already did it. I just have to upload it. So I guess I should say, yeah, you'll get your homeworks before Monday. You'll get them like today probably, but like they're not due, meaning like the TA like official timeline is like have the grades back to students on the Monday, by the Monday after, like the 1 week after they submit the homework. So anyway, but you'll get a numeric grade if you go into NYU classes and you look in your grade book. So just like refresh that. I'll send an email. I'll send an email that just says like, hey, homework 1 grades are posted. Cool. Early access for y'all. So yeah, causality, where we left off. Fundamental problem of causal inference, right? Which is the issue that it goes back to like David Hume, right? This like 18th century Scottish philosopher, if you want to like dig all the way back to the history, but the whole idea is just that he realized like the only coherent way to define like a cause, like X causing Y, would be that you would have to imagine 2 universes that are the exact same, and the only difference is that in one universe, like X happened, and in the other universe, X didn't happen, right? That's like, it turns out, if you try to like define causality, you kind of get stuck there, right? That's kind of, it just bottoms out at like Humean causality. And then that's the fundamental problem of causal inference, right? Is that we can't just like create universes like that. We can't just be like if I'm a drug manufacturer, I can't just be like, oh, okay, I'm gonna make one universe where I give Jeff the drug and another universe where I don't, and see if he's better in this universe, right? Like in real life, we only observe one of those 2, right? We either observe the universe where Jeff got the drug or the universe where he didn't, right? So yeah, we might think like, oh, well, then it's hopeless. We can't do anything causality. It's like a pipe dream. We can forget everything and run, right? We can just give up. I might just use this meme in every section ever because I think it's, I don't know why. I just think it's hilarious and the cheesiest meme I've ever seen in my life, but I love it. But no, don't forget everything and run. We're gonna face everything and rise, right? Because yeah, the point is like, what we can do is there like all these all these like statistical scientific researchers over the past 400 years have come up with ways of getting as close as possible to causality, right? So like, again, we've established causality, impossible to establish, right? Because you can't create new universes, counterfactual universes, right? But what we can do is we can create good comparison cases, right? Like we cannot compare like Jeff in universe where he took the drug and Jeff in universe where he didn't. But imagine if I had like a twin, right? Then what you could do is you could give one of us the drug and not give the other one the drug, right? And then you actually know that like almost like everything about these 2 people are similar in terms of like genetics and genetic predispositions and all that. And so the main difference between me and my twin, right, would be that one of us got the drug and one of us didn't. And so like we would know that if say I got the drug and I had like a better outcome, like I was cured of the disease, whereas like my twin wasn't, then again, we can't say, oh, the drug caused me the disease to go away, but it's like really close, right? Because it's like almost everything about these 2 people is identical, except one got the drug and one didn't, right? So that's kind of like the rule of thumb that you want to follow through like all this causality stuff is you want to compare, you want to get as close as possible to that like 2 universes that are the exact same, but in one X is this value and in another X is this value, right? X in this case being, sorry, the independent variable, like the thing you're manipulating, right? In this case, like whether they get the drug or not. And so I just wanted to mention this. It's not on the midterm or final, but like I think it's just literally like it's what clicked in my brain for the fundamental problem of causal inference when I was learning it. Is like there's this process called statistical matching, right? Which is what I was saying, right? Where even if you don't have twins, if you have twins, that's great. Like pair them off and give one the drug and don't give the other one the drug. But if you don't have twins, like just measure all this information that you can about all the people in your sample and like pair them, pair like the most similar people, right? And compare them, right? Is my internet going out? I see a message, your internet connection is unstable, which is like wild because I'm sitting in the middle of UC Berkeley campus, just like a major public research institution in the US, but that's cool. That's cool. Hopefully you can hear me. Okay. Thank you, Evie and Luca. Yeah, I'm just like, dude, I can't, like, I don't know where the Wi-Fi is. Why is it not in the center of campus? Anyway, let me just say in the chat if it goes out. Okay, cool. So great, not on the midterm or final, but statistical matching is just about that pairing process, right? Because that's as close as we're ever going to get to causality, right? Is like, we have two people and the only difference between them basically is that one got the drug and one didn't, right? That's like a thing, like people spend time, people develop algorithms and prove mathematical theorems and stuff about like how close or how well we can measure causality by doing these statistical matching procedures, right? So we don't learn statistical matching in this class, but like it's what comes into my head when I think fundamental problem of causal inference. Cool. But so with that said, it's like, why do we keep talking about experiments, right? Like, why do we think that they'll help over just, I don't know, just going around and like being like, oh, here, you can have the drug, you don't get the drug, like just randomly picking and then measuring how well the people with the drug do and how well the people without the drug do, right? Like, why do we have to spend so much time making sure that everything is controlled and that people are randomly divided between the treatment group, right, getting the drug, and the control group not getting the drug? Well, the key point goes back to the matching point, which is like the treatment and control groups have to be as similar as possible on average, right? And random assignment ensures that they are as similar as possible because there's no like bias in who's going into the treatment group and who's going into the control group, right? It's just flipping a coin. So you're not introducing any sort of like I use the term here. Oh, systematic. You're not introducing any sort of systematic difference between the treatment and control group, right? Which like maximizes the likelihood, right? Which makes it the most likely that you'll be able to do that pairing that I was talking about, right? Like, because if you were doing a drug trial, right? Say it's like a pill for diabetes or something, right? Like, but then you just put all the people with diabetes into the treatment group, you wouldn't actually like, you would be like, oh no, the drug must not work because I gave all these people the, like I gave this group of people the drug and I didn't give this group of people the drug. And the group of people that I gave the drug actually had diabetes more than the other group, right? But that's not a correct, like, it's not a valid treatment and control assignment, and therefore not a valid inference, because if you put all the people with diabetes into the treatment group, you're just like, it's probably going to be the case that at the end, like even if the drug did cure some of the people's diabetes, there would still be more people with diabetes in the treatment group than in the control group in that case, right? Because there's 0 people with diabetes in the control group. So I'm just saying, like, that's just an extreme example, but you just like need to make sure to the maximum degree possible that there's no systematic thing that's causing like, or that is leading to a certain set of people with certain characteristics being in the treatment group and being different from the control group, right? So yeah, it just does the work like for us if we randomize. It just says like, okay, I'm gonna like purposefully ensure that there's nothing but like a coin flip, right? That's determining who's in what group. There's nothing like, there's no statistically or socially interesting variables. Gets rid of selection effects. That's like kind of what I was talking about, where like if you only give people with diabetes the drug, then you're not actually going to be able to see whether it cures diabetes, right? And so selection, like zooming into that, you have selection issues if like you want to ask yourself the TLDRs, you want to ask yourself these 2 questions, right? You want to look at your experiment and you want to say like, why did this person end up in the treatment group and why did this person end up in the control group, right? The reason why experiments like handle this is that the answer is, oh, a coin flip. It's just random. It's not, there's no like socially relevant reason, right? We don't have to worry about, we don't have to correct for any biases between the two groups. But most things in life aren't that, like, are more messy than that, right? So like the Vietnam draft example that we've talked about in the class, but I don't, just to be like pedantic, I hate the phrase like Vietnam War, just because like we didn't just go and bomb Vietnam, we bombed Laos and Cambodia as well. So like most people in the world like study it, like just because I study the Cold War, right? It's my dissertation, like it's not the Vietnam War, it's the Vietnam, Cambodia, and Laos War that people just generally call Second Indo-Chinese War, right? Or second Indochina War, I wrote it down there. So, but yeah, for this class, we'll call it the Vietnam War. I just feel obligated to point that out. Is there was a draft, right? And so for the purposes of like this lecture, just imagine like the draft is random in the sense that they just flip a coin and they say like, if heads, all people with odd numbered birthdays have to go fight in Vietnam, Cambodia, or Laos, and all the people with even numbered birthdays don't, right? Or vice versa. If it comes up tails, then they switch it. The point being, like, it's a random assignment procedure, which is like pretty rare in the history and social science and stuff, right? So that's why I think this is the best example, or like a fascinating example of like randomization and how it lets you study things more systematically and find causality. Right, and what I want you to think about with that example is like, well, okay, why can't we just study people in the military versus people not, right? And so the other example I want you to think about is like the Iraq War, right? Like the current war in Iraq, which is like not a draft, right? People actually go and volunteer to fight in it, right? So the difference there has everything to do with selection, right? Because in the Indochina example, like people just don't have, like, people, you just flip a coin and that determines whether you go fight or not, right? Whereas in Iraq, there's selection. You actually have to say like, oh, I want to go fight there, right? And so the reason that matters for like causal inference is that men who join the military, yeah, sorry. So the difference is that so basically like in the US, like the way that the military works, like social scientifically, is just that like it's disproportionately poor people and it's disproportionately people of color, right? And so like it's not random assignment, right? Meaning like if you're poor, you are more likely to go and fight than if you are not. So when we get to, and I'll come back to that in like 1 second when we get to going from observational data to trying to make causal inferences, but just remember those two examples, right? Indochina draft, random whether you're fighting, right? Iraq War, not random whether you're fighting. And we'll see, we'll like dive into why that matters. But for now, like, why can't we just study the difference? Well, because then like we don't know whether it's fighting in the Iraq War that actually affects the outcome, right? Let's say like we're studying, oh, does fighting in a war increase your chance of getting diabetes or something, right? Well, but in the Vietnam case, we can actually say like, oh, there's no systematic difference between the people who fought and the people who didn't, besides like a coin flip, right? Besides, the only difference between them is the actual, like, did they fight or not, right? Whereas in the Iraq case, there's like tons more differences, right? There's like socioeconomic differences, racial differences, etc. And so in the Vietnam case, you can say like, oh, the change that made, say they find that like people who fight do get diabetes more often. They can say, oh, well, the only difference was like these people fought and these people didn't. That was the only systematic difference. And yet these people got diabetes at a higher rate than these people. Whereas in Iraq, you can't make that same inference because it's like, oh, it could just be that poorer people have diabetes more often, right? And that's actually like the case, right? Poorer people tend to get diabetes at a higher rate, right? So you can't, without that random assignment, you cannot like, and when there's selection, you can't pin down like what changed exactly, right? Like what variable led to the outcome. There's also the compliance issue, right? Because in all of this, I've just been saying like, oh, put people in the treatment and put people in the control, right? But, and again, reality, it's always more messy, because like you can't just, with a lot of experiments, you can't just put people in the treatment, right? People have to actually like comply with it, right? Have to say like, okay, yes, thank you, researcher, I will do the treatment, right? So like compliance is the degree to which people actually followed their assignment, right? High compliance is like most people who were in the treatment group actually got the treatment. Low compliance means like, no, a ton of people in the treatment group actually didn't get the treatment, and a bunch of people in the control group actually like went and low key like went around the rules and got the treatment, right? And so what problems might there be with compliance in the draft example? Well, that's like, you know, there was a thing called like conscientious objection to the draft, which is like, you know, people said, oh, no, I'm not going to do that. Like, if I get drafted, I'm not going to fight. I'm just going to go to jail, right? So that's called like being a conscientious objector status. I think you just sit in jail while the war goes on or whatever. Who's that? There's that boxer, Muhammad Ali, famous like boxer. He like went to jail because he wouldn't fight. He got drafted, but wouldn't fight in the Vietnam War, right? So it's not, that's an example where like they got the treatment, right? They got drafted, but they did not comply with it, right? They didn't actually go and do the treatment. So we can't like consider them in the group when we're considering the effects of fighting in wars on diabetes later in life, right? And vice versa, much more morbid case, there were tons of people who did not get drafted, but were like, no, I want to go like shoot people in Asia, right? And there's a whole books on this. Like, there's a book called like Revolutionaries for the Right about people who just kind of go to wars even when they don't get drafted, or wars that the U.S. isn't even involved in, and just, you know, participate. So that's an example of like they're in the control group, right? They're not drafted into the war, and yet they don't comply with the control, right? They actually do go fight. So they also mess up the like comparison of, oh, does going to war like cause diabetes because they didn't comply with their like placement in the draft, right? So cool. And then, but in all this, right, it gets even messier because in that case, at least, they were randomizing, right? Like the compliance was an issue, and but there's no selection, right? And because they were randomizing, but observational data is kind of like another step further from like the holy grail of causality, because, right, when you're doing like drug trials, or when in really rare instances like the draft, yeah, you can like randomize, but usually it's not that simple, right? Usually what happens is like you can't, yeah, as social science researchers, like you just walk up to a set of data. You just like kind of open up a piece of data set on your computer, and you're like, all right, let's figure out what's going on here, right? It's like observational data. And just to like be really precise about it, like observational versus experimental, that has to do with like who actually chose the treatment versus control separation, right? So treatment in the Vietnam case is like, oh, someone actually chose who gets drafted or not, right? I mean, they did it with a coin flip, but they chose the mechanism by which people got put in the treatment group or the control group, right? Observational data, you just like no one had control over it, right? Like, again, I study like the Cold War, so those are going to be all my examples basically. It's like, I can't go into history and be like, all right, let me see what history would have been like if Angola like didn't become a communist country, right? Like Angola didn't, the MPLA didn't win the Angolan Civil War. I can't do that, right? We only observe one, and it's very messy. There's like millions of factors. We don't know like what led certain countries to be like communist or not. So let's say, I mean, we have some idea, but like there's a million factors. No one's sitting there being like, all right, we'll flip a coin, and for each country we'll flip a coin, and if heads they're like aligned with the US, and if tails they're aligned with the Soviet Union, right? It's not that simple, sadly. So that's like most social science problems, right? And so on the one hand, like if you see this, but you can do an experiment. Like if you can do an experiment, you should. That's like rule number one, right? Is if you're a social scientist, or whatever type of scientist, and you're studying something and you can do an experiment to like manipulate the independent variable to see the effect on the dependent variable, like you need to do that, right? That's like because of all the things we've been saying so far, right? But on the other hand, like I said at the beginning, statisticians from the last like 4 centuries have developed fancy tools and techniques to help us, even if we we can never solve the fundamental problem of causal inference, but sometimes it's like double bad and we can't even choose the mechanism of like what people are in the treatment and control groups and how we get to compare, right? So in those cases, we have to take out like this equipment called like causal diagrams, which yeah, is just like a way to, yeah, it's just a way to, like it seems weird because we're drawing pictures and you think like, oh, that's not math, that's pictures. But actually, this is the main thing that statisticians, well, this is the main thing that statisticians who work on causal inference do, right? Is they worry about these diagrams like you see here on the right, which is like a posited causal effect, right? Meaning changes in X cause changes in Y, or changes in Z cause both changes in X and changes in Y, right? That's what this is telling us. Yeah, go into the chat. Yeah, great. So control variables for observational studies. Well, that's the point, right? Is that we still have treatment and control for sure. You always have treatment and control. Like that's what you're doing when you're trying to see like do changes in X affect Y, right? Meaning you're trying to see if like X equals 0 means control and X equals 1 means treatment, and you're trying to see if changing X from 0 to 1 causes Y to be different. It's not just for experiments. Yeah, going back to the chat again, it's not like the point here is that we are doing all this stuff. We are making these pictures and stuff because we want to figure out how to take our observational data and make it as close as possible to the holy grail of experimental data, right? So like we're using these diagrams to like plot out the different variables that we need to control for in order to get the gold standard of a controlled experiment, right? So this is just terminology. This slide, right? It's causal terminology for observational studies. It's just introducing this terminology because I'll show you in a second. I have like 3 examples right after this. So okay, in the chat. So we can introduce more variables for both. Okay, to answer the question, the question in the chat is, can we introduce more variables for both experiments and observational studies? It's a little tricky because in an experiment, like if you're designing an experiment, then yes, you can include whatever variables you want, right? Like because you're designing it and you can measure, like you can take the people, right? You sample people, you bring them into the lab, and then you measure stuff about them, right? But after the fact, yeah. So then mid-phase or after the start of it, yeah, in the chat. The question is like, can we do that in the middle of the experiment or after the start of it? You can, but it's not optimal, right? Meaning like you lose a lot of the properties that are like that are the nice things about experiments that we just talked about in the previous slides, right? So like, how do I put it? Like if you read a scientific paper, right? Like the best ones, like the ones published in like Science, right? Like the journal called Science or Nature, these like big science journals, like they're not gonna change anything in the middle of the experiment. That's like very, sketchy. There's actually a thing called like a pre-registration plan, which is where like before you even publish the paper or do the experiment or anything, you submit a plan saying like, here are the variables I will measure. Here's how I will assign treatment and control, blah, 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 right? That's like a big thing that's been a big thing in like biomedical research, for example, and it's becoming a big thing in social science. Like there's journals that require you to submit a pre-registration study, right? So yeah, you don't want to change it mid-experiment, but like if your question is like, can you? It's like, yes, you can. but you're gonna have to do all these statistical corrections and stuff. And most, most researchers will want you to just redo it. Like yeah, okay. Let me just finish that. So like literally people that I've like worked with, right, in like my department at in political science, like at Columbia, I've like been part of studies where we just had to redo the entire thing because we realized like we forgot to measure a variable, right? So yeah, like you can change it mid-study, but it's most of these like big journals, they're not gonna accept that because it's like you want to pre-register it so that researcher bias isn't like changing the experiment as you go. It's like kind of outside the scope of this class. For this class, you can just imagine like experimental designer. They design things before they do the experiment, and then they do the experiment, right? Okay, so then going back to the chat, could you answer the question again? Yeah, sorry. The question is like, the issue is like with the wording of like control variables or observational studies. It's like, they're all just variables, right? And the point is that when you're an experimenter, you choose like who gets x equals 0, right? Say the control, like who's in the control group and who's in the treatment group, right? So you take some people and you say, for you, x equals 0. And you take other people and you say, for you, x equals 1, right? But for for observational data, no one is like making that choice, right? There's no like world like researcher. Again, let's go to my dissertation, right? Like there's no world researcher who's deciding like, aha, I will flip a coin and I will assign some countries to control group and some countries to treatment group, right? It's like, no, in observational data, the variables are just all there. And we have to use this type of like terminology. We have to put it in these statistical frameworks to establish like, okay, we're gonna call this we're going to call like this the control group, we're going to call this the treatment group, we're going to call this the outcome variable, right? And we're going to call we're going to study these variables as confounders, right? That's why like this diagram should always be in your head, right? Because yeah. So
question is that
sorry,
sorry.
I'm in the middle. Yeah. What's up? Sorry.
My question is that, so we can draw causal reference in observational studies if we introduce more variables like control variables, right? And
I see what you're saying. Yeah, I see. Go on. Yeah.
yeah, and also in experiments, can we directly draw causal inference out of these experiment, right?
Totally. No, these are great questions. No, thank you for clarifying it. That makes, yeah, these are great. These are like the questions that you should be asking. Like the questions that you're asking are like that is the why we're teaching this, right? Which is like, okay, so first question, well, let me do them in reverse order. So, because the second question was, can we draw sorry, okay. I think I'm doing them in the right order. First question was, can we draw causal inferences even though we only have observational studies? Yeah, like that's what all this fancy stuff here is for, right? All these like making these little graphs and like the statistical methods where that take these graphs and measure, the arrows and the boxes in them, right? Those are so that you can go from observational data, but still make causal inferences from it, right? So it's like you're taking observational data and you're kind of like molding it, right? To make it look as much as possible like experimental data. So like the example would be causal versus, yeah. So the example would be like, say that, so in the world, right, again, I just have to do my dissertation because it's just in my brain. Like in the world, there were a lot more countries aligned with the US than with the Soviet Union, right? So actually like the treatment and control group aren't balanced in that case, right? If you can't tell, the treatment here is like a country deciding to become communist or whatever, or not deciding, but they get invaded by the Soviet Union and they become communist. in that case, like no one chose it beforehand. It just happened because of history. But the point is like maybe like 75% of countries were aligned with the US and 25% of countries were aligned with the Soviet Union. And so we have to like mold it. We have to like do transformations because it's observational data. We don't get a balanced treatment and control group, but instead we have to say like, let's downweight the data from the countries aligned with the US and let's upweight the data from the countries aligned with the Soviet Union so that we can get like a balance, right? Like a 50-50 balance, right? It's just stuff like that, right? We're just transforming the observational data to make it look as much as possible like a controlled experiment. But that's why it's like harder to derive causal inferences from observational data than experimental data, but you can do both. But then the second question is kind of a different type. It's like an epistemological question if you wanna, it's a fancy, pretentious word. It's like a question of like, what like scientific method, right? The point being like, we cannot ever like prove causal claims because we can't prove any claims because science is based on falsification, right? You can only disprove things. But for experimental studies, we are as close as possible basically to solving the fundamental problem of causal inference. Whereas for observational studies, we're like even a step further, right? Here's the holy grail, like proving a causal claim. You can never do that. Here's like the closest we'll get to the holy grail, which is randomized controlled experiments. And then here we're like another step away, right? Which is observational. And we have to like manipulate the data and do weird statistical tricks to try and make it look like experimental data and like take into account the factors that make it not experimental. So, okay, I'm gonna go on, but like happy to talk about that stuff in office hours or piazza. Yeah. What's up? What's the question? Okay. I heard someone saying something, but yeah, feel free to ask on piazza or email me your office hours or anything. Oh, cool. Yeah, no, you're welcome. Yeah, those are such good questions, like seriously. Cool, and then I just included these example slides next because like I literally didn't cherry pick these, like literally they just popped up in articles that I was reading over the past few days and I was like, oh, I should put these in the slides. So like here's an example, like an article that just came out on this blog called Phenomenal World. I guess full disclosure, it's like the company that I work for, it's their blog, but I don't really like, I'm not the editor. I just write for them as well. But it's a great article and it's like talking about like different theories of race and causal inference. Like, you know, in the US, like what's the impact, what is the causal effect of your race on like your earnings in the future, right? It's a whole article. It's not trying to like argue that any of these theories are correct. It's like a meta article talking about like, hey, as social scientists, what we need to do is we need to construct these causal diagrams, right? And like compare the theories, right? So in this case, we're like, oh, I think like this is a theory, right? Every like theory corresponds with a causal diagram. Well, every good theory, right? There are non-falsifiable theories that don't correspond with the causal diagram, but every like good theory, you know, you can make a diagram like this. And so there's this whole article, it's linked here, and it's just talking about like, okay, well, are the three most salient variables race, education, and wages, or do we have to include position and segmented labor market, which is just the idea of like there's white collar, blue collar, and white collar jobs, and there's like low skill and high skill jobs and stuff. Like if we want to make a causal theory about race, like which of these is better? It's just an article about that. Okay, so in the chat, the question is, can we know the causal effect by calculating endogeneity bias? Endogeneity bias. I'm not even sure I remember what that is. Like it's sometimes I'm really bad at remembering like the buzzwords. Well, it's more just like because I'm from like computer science, not political science originally, so my brain is like doesn't use the social science words a lot of times. So I might know what endogeneity bias is, but I don't know that like phrase. But we cannot ever know the causal effect, like ever. Like so, if we start the question with like, can we know the causal effect by blank? The answer is always no, because we can't know the causal effect, right? But what might answer your question is like, we can correct for the biases, right? the additional biases that might come in an observational study that wouldn't be there with a randomized controlled trial. Yeah, sorry, I don't, like there's no math that you can do. It's not a mathematical question, right? It's the epistemological question of like, can you infer causality, right? Meaning like the epistemological question is like, no amount of math that you could ever do will let us like show causality. What you're talking about, right? When you compute things like this, like the endogeneity bias and correct for it. Oh, I think I know what this is actually. I think I know what this is. Thank you for writing out the equation. I think I'll have to like move on after this. Like I think what this is you're talking about like you're correcting for the different that different like subsets of the data have different variances, right? Because here this equation gamma 1 equals beta 1 plus covariance xi ui divided by variance of xi. All that stuff, all that math stuff, it's just it's a mathematical tool, and it's the thing that I'm saying of like taking the observational data and trying to make it look like experimental data, right? So I'm saying like even if I don't necessarily know the specific, like there's a million different like mathematical corrections, right? Going back to this slide here, right? There's a million different things. Statisticians over the last 4 centuries have developed all these tools and techniques to help us kind of turn observational data into causal. So yeah, any math stuff is like that, right? It's probably stuff that you don't have to worry about if you do a randomized controlled experiment, but you do have to worry about for observational data. So yeah, by computing this endogeneity bias and like dividing it out, basically, yeah, we get closer, right? We make our observational data look more like experimental data, and we correct for the biases coming from the fact that it's observational instead of experimental. So yes, perfect. Okay, in the chat, yes, you got it. Because in the chat, the message is, we can't draw a causal inference anyway. All we can do is make a more accurate estimation. That's exactly it. I should have just put it that way at the very beginning. Yeah, no, it's perfect. I'm glad you put it that way because yeah, we're never, like, I don't know, I was like a math major, right? So I always have all these mathematical things, like diagrams in my head that probably normal humans don't have. But you know, like an asymptote, if you ever learned like in calculus or pre-calc, like an asymptote, I think of like causal inference is like this asymptote. We're never gonna reach it, but we can get really close to it by doing a lot of work and like correcting the biases, right? We can get more and more accurate estimations. Yeah, cool. And then I'm just showing these examples because like, yeah, it'll literally just pop up in like papers that you read or blog posts, like if you do social science stuff, right? This one is for like a causal graph of domestic violence. And the only reason I wanted to include it is because you'll see it has these like minus signs and plus signs. So it's just a version of this from Erling's slides, but instead of just arrows, right, with like this is saying like, oh, there's some causal effect of X on Y. That's what this theory is saying. This is like a more specified, a more like filled out theory, because the minus signs and the plus signs here are just saying like an increase in AP causes a decrease in PLS. I don't remember what this means. I'm really sorry, but you can click the link and look at it. DV is domestic violence. So let's just say whatever AP is, an increase in AP causes a decrease in domestic violence. So yeah, I didn't read the whole paper because you can't read whole papers because you have to read like 20 a day to do a PhD, and I'm lazy, I guess. So I just like skimmed it and I saw this and I put it in the slides. But the point being, like, you'll just see these causal diagrams all over the place, right? Domestic violence, you cannot well, hopefully you're not doing an experiment, right? You're not randomly assigning people to be victims of domestic violence, hopefully, right? And so instead you use these causal diagrams to like transform data, observational data on domestic violence, try to analyze it causally, right? Cool. And then here's the last one, which is like police shootings, right? This is a researcher who, like, I completely don't necessarily like their theory, right? And yet, like, the beautiful thing is that they, at the very beginning of this little publication here, they put the causal diagram of like their theory, right? Like, they're like, I am measuring the causal effects of, you know, police bias and blah, blah, blah on police shootings, right? And it's like, if all social scientists just put their theories and diagrams like this, we could see like I could make a different diagram and I could say, oh, here's my theory. And then we could go and look at data and see like, you know, plug the data into the models basically and understand why like I might draw a different conclusion about police shootings than this other research, right? It has to do with what data is going into which of these little slots and which arrows in the causal diagram, right? Cool. All right, so that's all for causality. Like I'm just zooming because for time purposes, but tons to talk about there. I'm just gonna real quick talk about Python sequences, and then there's also Python libraries, but we're actually very close to the end because the Python libraries slides are just there kind of for you to look at on your own time. Meaning I'll get to, in like 3 minutes, I'll get to, yeah, I put an example slide for each library that we use in this class, like just a slide showing code using it. But you can just look at that at your own time. So I'm just gonna finish Python sequences and then we're done. So where we left off 2 weeks ago on Python sequences, right, was we had learned the word sequence because we did this thing, we took a string, right? In this case, my string is JEFF, and then we took a float, 5.5, but you can imagine like instead of 5.5, like 2.7839216, right? And if you try to multiply a string by a float, Python's gonna be like, I don't know what that means, right? When you multiply a string by an integer, by an int, it can say, oh, okay, I'll just repeat it that many times, right? So Jeff, this string JEFF times 5 would just repeat 5 times, right? Jeff. But it wouldn't know how to say like, how do I repeat a string 5.5 or 5.23687 times, right? But we saw like it says we can't multiply sequence by non-int, right? And it's like, wait, why? What's a sequence, right? And we learned, I talked briefly about how like a string is a sequence because it is just a collection, an ordered collection of letters, right? In this case, like the first thing in the sequence is capital J, second thing is lowercase e, third thing is lowercase f, fourth thing is lowercase f, right? And so going to the slides now, this is from Prof. JR's slides, like all that we've been learning up to now have been these different types, right? And then sequences are just ways of agglomerating, but like creating collections of these types, right? Cool. And so like my TLDR is that lists are just these ordered sequences of anything, including lists themselves, which gets very confusing, right? So like in this case, it's a list with 3 elements, right? The first thing is the int 1. The second thing is the string with the letters O, N, E. And then the third thing is the float 1.0, right? So that has 3 elements. But what's weird is that the elements can be lists themselves, right? So in this case, as like a human, when we look at this, we might think like, oh, it has 1, 2, 3, 4, 5, 6, 7, 8, 9 elements, right? But actually, no, like as far as Python's concerned, this list just has 1, 2, 3, 4, 5 elements, right? It has my basic list, which is just an element. It doesn't care what the type of the element is. It just says, all right, this is the first element in my meta list. And then the int 2, then the string TWO, then the float 2.0, and then another list, right? So that's 5 things as far as Python's concerned, even though like if you go through, like if you look at it as a human, it might look like 9 elements, right? It's a list with 5 elements, but 2 of the elements are lists themselves, right? And so it's not putting lists inside of a list, right? Like nesting lists is not the same as combining lists into combining the elements of a bunch of lists. And that's where the plus sign comes in with lists, right? We learned how the plus sign has different meanings for different types in Python. For lists, the plus sign just says like, take all the elements from this and then add all the elements from this and then add all the elements from this, right? Each plus sign just means add all the elements from, right? So in this case, we actually do get 9 elements in the list, right? Because we say, take my basic list, now take everything in this list and add it on to my basic list. And then take everything in this list and add it on, right? And so in that case, like each time we're like appending, right? The word is like append. So now we had a list, my basic list, which had 3 elements, and then we said plus, which adds 3 more elements, and then we did another plus, which adds 3 more elements, right? Not the same as putting the list as a list element inside of the list. Just take some time to look at that. It's scary, but yeah, the reason that we say an ordered instead of an unordered, like the reason we say an ordered sequence is because there are unordered data types in Python, which you don't have to worry about, but I just wanted to show you, like, unordered things don't preserve the ordering, right? So in this case, we might say, oh, I want a list, right? But the first thing is 4, the second thing is 3, the third thing is 2, and the last thing is 1, right? But there's a data type called a set in Python, which just throws away the ordering. It doesn't care about the order, right? There's no like notion of ordering of the elements in set. It's like a big bag of things all jumbled together. You don't have to worry about sets, but I'm just showing you why we say ordered. And then arrays, right? In this class, we kind of make a big deal out of it, but I think we don't have to, because an array is just a fancy list. It's just like Python wasn't made for doing math or statistics, right? Python was made for like just programming stuff. So they didn't put a bunch of math functions that you could do with the list. But in this class, because it's data science, we do want to do a bunch of math with the lists, right? So created this thing called like NumPy, right? I put what happened here, even though it doesn't show up, because if you run this, you'll get an error, because Python will say, what's NP? I don't know what NP is. And that's because you have to remember to import NumPy first. That's right. So once you import NumPy as NP, talked about that in lecture, then you can use this np.array function. And all it does is it takes a normal Python list and it converts it into a fancy list, an array, right? And now once we do that, suddenly we can do things like compute the mean, right? Like ordered list here, that's a regular Python list. So you call .mean and Python's like, I don't know what you're talking about, dude. There's no, lists don't have a thing called mean. There's no function called mean for lists, right? But if we take the array, we take the NumPy array, suddenly we get all these nice math functions like mean, right? Which is the average value in the list. So cool. That's all a NumPy array is. That's a detail. I just wanted to point out that like there's 3 different types of brackets and they're called different things in different countries and blah, blah, different cultures, blah, blah, blah. So the only one you need to worry about in this class is these square brackets, right? Because the square brackets are telling Python, make a list, right? If you start this square bracket and then you start writing things with commas in between them, Python will interpret it as a list, right? You don't want to do the curly brackets or the parentheses because you'll get these weird other types that you don't need to worry about. Cool, and then we're at the end because this is just an overview of the 6 libraries that we use in this class and how you import them. And it's just like, yeah, we have math with arrays with NumPy, we have math with tables, 2D arrays and pandas. Matplotlib is for visualizing the data in arrays and tables. Stats models is for doing statistical hypothesis testing, right? Like actually testing, you know, what's the relationship between X and Y statistically. Seaborn is for visualizing the stats models tests, and then scikit-learn is just fancy machine learning things. And all the slides after this are just 1 slide per library, so you can go through this. So I'm so sorry for going over. But yeah, hopefully you have a good weekend and I covered some stuff. And please bother us on Piazza and email because, yeah, otherwise we, like, feel free to, what I'm saying is feel free to post. I'll figure out some way, but there should be a way for you to anonymously tell me if I'm going like too slow or too fast. But even without the anonymity, like I won't be mad at you, I promise. Just, you know, it's genuinely helpful. I think it's a little too fast right now, but it's because I did stuff out of order, kind of. But anyway, in the future, I will try to put less stuff in the slides. But now we are caught up. Cool. So I hope you have a great weekend. And oh, like I said at the very beginning, like maybe right after this, if my laptop doesn't run out of batteries, I will upload your scores. So hopefully you'll have them like tonight. But technically, like they are due from TAs to the students by exactly 1 week, 7 days after the homeworks are submitted. So, cool. Bye. Great weekend.